Imagine a world where electricity was not just something we produce more of, but something we use far more wisely. Picture massive data centers humming day and night, processing artificial intelligence so advanced it can simulate human thought. Think about electric cars charging, aircraft flying without jet fuel, and high-speed manufacturing lines churning out products for billions. In every corner of our modern lives, electricity has become not just important, but essential. And yet, the world is approaching a crossroads. The amount of electricity people want and need keeps climbing at a pace no one expected. It's not just about switching on a light or charging a phone. It's about powering cities, industries, vehicles, and technologies that weren't even imagined a decade ago. The challenge today is not just making more electricity, but making electricity used smarter, more efficient, and more reliable. And at the heart of that challenge lies a tiny piece of technology that most people have never heard of: a power module. In the laboratories of the National Renewable Energy Laboratory, NREL, in the United States, a team of researchers believed they could change the game. The result of their work is a breakthrough so promising it might transform how the world uses energy. They call it ULIS, the Ultra-Low Inductance Smart Power Module. Before we dive into the story of ULIS, let's understand the problem it was built to solve. Electricity doesn't flow through wires and machines by magic. It must be controlled, regulated, converted, and shaped to fit the needs of different devices. When you plug in your phone, when a car's motor spins, or when a grid station sends power across the country, there are hidden electronics doing the work in between. Power modules are like the traffic controllers of electricity. They sit inside converters and power electronic systems and regulate how electricity moves from one place to another. Without them, energy would be chaotic and unusable. These modules take high-voltage electricity and transform it into the right form and speed for devices to use. But there's a problem. Older power modules are inefficient. They waste energy, they heat up, they add weight. And as the world demands more electricity for intense applications like artificial intelligence servers or electric aircraft, those inefficiencies add up. Enter the researchers at NREL. Rather than simply build a slightly better power module, they asked a bold question. Can we completely rethink the design so that it wastes far less energy, works faster, and costs far less to make? At the start of the ULIS project, the team knew that the limitations of existing modules came down to a few key challenges. Parasitic inductance, a kind of resistance that slows down electrical current and wastes energy. Size and weight, traditional modules are often bulky and heavy, limiting where they can be used. Cost and complexity, manufacturing high-performance modules can be expensive and slow. Parasitic inductance might sound like a technical term, but think of it this way. It's like friction in a machine. When you try to switch electricity from one form to another, that friction slows things down and burns off usable energy as heat. The more power being converted, the bigger the problem becomes. The ULIS team decided to tackle this problem head-on. Their goal? To build a module that could handle huge amounts of power, switch electricity rapidly and cleanly, and waste as little energy as possible. So, they started from scratch. In most power modules, semiconductors and circuits are stacked inside a box-like package. This works well enough, but it creates long electrical paths, high inductance, and inefficiencies. Instead, the NREL team invented something completely different. Their new design spread the circuitry into a flat, octagonal shape. Instead of stacking like layers of a cake, the components lie like spokes on a wheel. This layout dramatically shortens the paths electricity must travel, reducing parasitic inductance. The enemy of efficient power conversion. The result? The ULIS power module can achieve 7 to 9 times lower parasitic inductance than the best power modules available today. That means it can switch electrical current extremely fast and with far less wasted energy. In practical terms, switching electricity quickly and efficiently means the module can convert power in ways that fewer electrons are lost as heat, and more of that electricity ends up doing useful work. ULIS doesn't just move power, it unlocks it. ULIS isn't just better at moving power, it's also smaller and lighter than its predecessors. When a power module packs 5 times the energy density into a smaller package, the possibilities are enormous. Imagine electric vehicles with lighter, more efficient power electronics. Imagine data centers that consume less energy and produce less waste heat. Imagine aircraft powered by electricity that can fly farther and more safely. And imagine power grids that use less fuel and produce less pollution. This leap forward isn't just theoretical, The ULIS module is rated at 1,200 volts and 400 amps, meaning it can handle serious amounts of power suitable for heavy-duty applications. But that's not all. The researchers engineered the module to be more reliable in extreme environments. It includes systems that monitor its own health and can even predict component failure before it happens. That kind of self-diagnosis is crucial in high-risk situations like aviation or military vehicles, where failure is not an option. When you innovate something as fundamental as a power module, you don't just change its shape, you change its materials. Traditional modules bond copper directly to rigid ceramics to conduct electricity and manage heat. But the ULIS team found a better way. They bonded copper to a flexible polymer material called Temprion, creating a thinner, lighter, and more adaptable structure without sacrificing performance. Why does this matter? Because it makes the module easier and cheaper to build. Instead of complex, time-consuming processes that can cost thousands of dollars per unit, ULIS modules can be manufactured for just hundreds of dollars with widely available equipment. That's a profound shift in how power electronics can be produced. On top of that, the researchers made ULIS capable of wireless communication, meaning it can be controlled and monitored without physical cables. This modular, Lego-like design allows it to be integrated flexibly into many different systems, from power grids to vehicles to advanced aircraft. Now, let's step back and see the broader picture. Electricity demand is exploding. Data centers that power artificial intelligence and cloud computing consume massive amounts of energy. Transportation, from electric cars to electrified aircraft, puts new strains on power systems. Advanced manufacturing lines demand stable, efficient power, and as nations pursue cleaner energy sources, they need smarter ways to capture, convert, and transport that energy. In this world, simply building more power plants, whether solar, wind, or nuclear, won't be enough. The key lies in getting more energy out of the energy we already produce. Improving efficiency becomes as valuable as expanding production. That's where ULIS shines. By reducing waste, improving switching speed, and shrinking size, it packs more performance into less space and cost. Let's look at a few areas where ULIS could make a real difference. Electric aviation, aircraft powered entirely or partially by electricity, is no longer science fiction. Engineers are designing eVTOL vehicles, flying taxis, and electric planes that could change how people travel. But flying demands efficiency and reliability. Every kilogram of weight matters. Every watt of power must be used wisely. ULIS, with its high power density and reduced weight, could enable electrical systems in aircraft that are lighter, faster, and more reliable. And its self-monitoring capabilities could improve safety in systems where failure is not an option. Electricity doesn't travel from generators to homes and businesses in a straight line. It is transformed multiple times along the way, from high-voltage transmission lines to local distribution networks. Each conversion step introduces loss, heat, resistance, inefficiency. ULIS fast and efficient switching means more of that electricity is delivered where it's needed, not wasted along the journey. This could lower costs for utilities, reduce waste, and make grids more efficient overall. Imagine a data center powering millions of users, AI systems, and cloud services. These giant centers use enormous amounts of power and produce significant heat, requiring cooling systems that consume even more energy. If the power electronics inside those centers became far more efficient, the net savings in energy could be huge. ULIS offers a path to doing just that, squeezing more usable electricity out of the same supply. So what does this all mean? The story of the ULIS power module isn't just about a tiny piece of electronics. It's about a shift in how humanity approaches energy, not by creating power alone, but by harnessing it with far greater intelligence and efficiency. Instead of asking, how much electricity can we generate, we can ask, how can we use the electricity we already have more wisely? ULIS is one of the first answers to that new question. By reducing waste, improving performance, and lowering cost, it could accelerate the transition to cleaner energy, smarter machines, and a more sustainable technological future. In a world where energy demands continue to rise, the smallest innovations sometimes hold the greatest power. And in labs at NREL, a tiny power module called ULIS may be one of the most powerful innovations of all.